Hi everybody, today we are going to talk about two variable linear systems. So today we're going to focus on the elimination method. So the main goal of the elimination method is to eliminate one of your variables, and you can do this by creating opposite coefficients for one variable. So sometimes this will happen naturally, or you will have to multiply one or both equations to manipulate the coefficients. Then you add the equations vertically to eliminate, and then you can solve for the other variable. And once you have one, you substitute it into either original equation to solve for the remaining variable. So here's a quick example. So our goal is to either eliminate the x's or the y's. So I see that I can eliminate the y's, but I will need to multiply both sides of my second equation by 4. So I'm going to rewrite my first equation. And when I multiply by 4, I have two coefficients that are opposites. So now I can add vertically and my y's will eliminate. So I get 22x equals negative 11. So x will equal negative 1/2. Now that value I can go back and substitute it into either the first or second. I'm going to substitute it into the first one so it's a little easier to simplify. So we get negative 4y equals negative 6, so y will equal 3/2. And then write your answer as an ordered pair, and we are done. Alright, so go ahead and pause the video and give this problem a try. Okay, so you can see here that I chose to eliminate my y value, so I multiplied the second equation by 3, and then you get x equals 4 and y equals 3. Alright, here's an example where we're going to need to multiply both equations. So I think that I'm going to eliminate the y's. However, you could absolutely eliminate the x's and get the same answer. So I'm going to multiply my entire first equation by 4, and I'm going to multiply my entire second equation by 3. So we have 20x plus 12y equals 36, and 6x minus 12y equals 42. So when I add up vertically, we get 26x equals 78, so x equals 3. And then I can substitute that into either equation. Let's substitute it into the first equation. So we get y equals negative 2. Alright, go ahead and pause the video again and give this problem a try. Okay, so here you can see that I decided to eliminate my x's. However, if you eliminated your y's, you should end up with the same answer of 3, negative 1. Alright, so now we're going to talk about how to approach a problem where we have decimals. It's actually really easy to do. The first thing we're going to do is clear the decimals. So I'm going to multiply both equations actually by 100, which will move our decimal places over 2 spaces, and then we have something that's much easier to work with. And then from here, it's just that same method we just talked about. So we are going to need to multiply both of our equations here. So I'm going to multiply the top equation on both sides by negative 3 and the bottom equation by 2. So we get negative 6x plus 15y equals 114, and then 6x plus 8y equals 208. Now we're going to add vertically. So we get 23y equals 322, and if we divide both sides by 23, we get y equals 14. So there we can go and substitute it into either of these equations. We don't need to use the original because these are completely equivalent. So we get 2x minus 5 times 14 equals negative 38. And we should end up with x equals 16. All right, go ahead and pause the video and give this one a try. Okay, so clear your decimals, and then I multiplied the top equation by negative 2 and the bottom equation by 3 to eliminate my x's. You should end up with 9, 12. All right, so now I want to take a second and talk about the possible outcomes for linear systems, because you won't always get one nice simple solution. So of course it is absolutely possible to get one solution. So really it's just two linear equations that are crossing at some point. But it's also very possible to get no solution. So that occurs when we have two parallel lines, or two lines with the same slope, because those lines will never cross. However, it's also possible to get infinite solutions, and that really occurs if your two equations actually make the same exact graph. And we are going to talk about how we're going to write these answers. So let's look at this first example. So here, let's try solving this using the substitution method. The elimination method. I'm going to multiply my top equation by 2. I'm going to just put it right underneath. So 2x minus 4y equals 6. So when we do this, both our x's and our y's actually cancel out, but then we get something that says 0 equals 7. So if your both variables cancel out and you end up with a statement like this that is just not true, this is actually when we have no solution. And actually, if you rewrite both of these equations into slope-intercept form, you'll see that they actually have the same slope of 1/2, which means they are two parallel lines, which is why they are never crossing, hence no solution. All right, go ahead and give this problem a try. So same idea here. If you use elimination method, you end up with a statement 0 equals 11, or some other statement that just is not true. So this is what it looks like when you have a no solution system. Now let's have a look at this problem. So maybe from the get-go you notice that these two equations, while they look a little different, they actually make the same exact line, because if you multiply this top equation by 2, it's the exact equation as the bottom one. But let's say you don't catch that and you decide to multiply this by negative 2 and you use the elimination method. Here's how it looks different than no solution. Here, your variables once again cancel out, but you have a statement that is true. 0 equals 0. So when that's the case, we have to find a way to still, We have to still find a way to write some sort of answer. So we do have infinite solutions, but there is a way that we can relate our x value to our y value. So how it works is you actually either set x or y equal to a. So let's say that I'm going to let x equal a. So then I'm going to go and substitute that into maybe my first equation. So we have 2a minus y equals 1. Now I'm trying to solve for y, so I can also write y in terms of a. So if I add y and subtract 1, I get y equals 2a minus 1. So I actually write my answer like this. So this is kind of a template for all of the possible solutions that you can have. So a is just going to be some constant. So you can actually go and plug in different a values and it will give you a list of possible solutions. It's also a nice way to show the relationship between x and y. So this is saying that your y value is always going to be twice as much as your x value minus 1. All right, so go ahead and pause the video and see if you can give this problem a try. All right, so here, once again, your variables cancel out, but you get a true statement, 0 equals 0. So now we have to find a way to relate x and y. So here I'm going to let x equal a, and then I substitute it and I solve for y, putting it also in terms of a. So this should be your final answer. So now you know what it looks like if you have a no solution case or if you have an infinite solution case, and how we should write our answers. Now we're going to try a couple word problems. So this problem says an airplane flies into a headwind and it travels the 2,000-mile distance between Florida and California in 4 hours and 24 minutes. On the return flight, the airplane travels this same distance in only 4 hours. Find the airspeed of the plane and the speed of the wind. So we can use the question to help us define our variables. So I'm going to call it R1 and R2. I'm going to say R1 is the plane speed, and I'm going to say R2 is the wind speed. So we're actually going to use our distance equals rate times time formula to help us create a system of two equations. So you can see that the distance is actually the same for both trips. So we can say 2,000 miles. And let's start with the flight there. So it says on the flight there, it takes them 4 hours and 24 minutes. So that's going to be our time, but we have to find a way to describe the rate. So the reason why it's taking longer to go there, it's taking 4 hours and 24 minutes, is because it says that they're flying into a headwind. So this is going to be key. So what's happening is the plane is flying forward, but the wind is actually kind of pushing back into it, slowing it down. So the overall speed is going to be R1 minus R2. The speed is slower and the wind is actually slowing it down. And then we're going to multiply that by the time, which is 4.4. So I converted my minutes into a decimal So that's my first equation. And then for the flight back, so we know that that distance is the same. But this time you're flying with the wind. So imagine that the plane is traveling this way, but the wind is also traveling that way. So the plane actually gets a little boost. So the speed is actually going to be R1 plus R2. So the wind is kind of helping it. And then the time is 4 hours. So now we have our system of two variables. So we actually have 2,000 equals 4.4 R1 minus 4.4 R2, and then we have 2,000 equals 4 R1 plus 4 R2. So that's the setup for these types of problems, and then you would just solve the system using either the elimination or substitution method if you like. But the thing you need to be careful about is setting up the way you describe the rate. So remember, if you're flying into a headwind, or if you're like sailing against a current, you're actually going to have a slower rate, which is why it's R1 minus R2. And if you're flying with the headwind, it's going to kind of give you a boost, so it's R1 plus R2. But other than that, it's just distance equals rate times time. All right, so see if you can pause the video and give this problem a try. So this problem, it's the same general setup. We have the R1 and an R2. So on the flight there, it's R1 minus R2 because you're flying into the wind, and on the way back, it's R1 plus R2 because you're flying with the wind, so you're getting a little boost. And then you can see I solved this one using the elimination method, and you should get 525 miles per hour for the airplane speed and 25 miles per hour for the wind speed. Okay, the last type of problem that you'll see is a supply and demand equation. So we have a supply and demand function for a video game console, and P is the price per unit, and X is the number of units that are sold or produced. So they want us to find the equilibrium point. So for supply and demand, the equilibrium is going to occur wherever supply is equal to demand. So imagine a scenario where the price is set just perfectly, where the number of products that a company is encouraged to produce is exactly the same as the number of products consumers want to buy. So since supply is equal to demand, well, that means that we can just take this first function and set it equal to the second one. So you can literally just say 90 plus 0.00002x equals 180 minus 0.00001x. And then we can just solve. So we can isolate x and solve. So we should get 0.00002 3x equals 90. So x is going to be 3 million, and that's the number of units. And then we're going to substitute that into either function to find our price. And our equilibrium price should come out to $150. So you can either write it as a complete answer. So this is the equilibrium production, and this is the equilibrium price. Or you can write it as a coordinate. You can say 3 million and then 150. All right, that is all for today. Thank you for watching.